JMB, how are you all? I hope you all are great. Welcome back to my YouTube channel. My name is Ranpara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of the Technology, ROPA. So in today's lecture, we are going to continue the solution of the industrial numerical example, which we have started in the previous lecture, lecture number 14, right? So let's get started. In the previous lecture, where we have calculated the volume of the batch reactor by using the fundamental concept of the space-time, right? So the way of calculating the volume of the batch reactor by using the fundamental concept of space-time is conceptually correct, but partially incorrect, right? So we need to opt a different way, the actual way of calculating the volume of the batch reactors, right? So in today's lecture, we'll understand how we actually calculate the volume of the batch reactors, right? So let's get started. Okay, so in the previous lecture, lecture number 13, where we have calculated the volume of the batch reactor, right, for the zeroth order reaction, okay, by using the fundamental concept of the space-time. Okay, so in today's lecture, which was conceptually correct but partially incorrect, right? So in today's lecture, we are again I'm again going to explain you the actual way of calculating the volume of the batch reactors for the zeroth order reaction, for the first order reaction kinetics, right? So let's get started. Now let's say, so how to start? Okay, we need to understand that from where we need to begin. Okay, so let's say we are trying to understand and design the volume of the batch reactors, right? Which means, let's say, for the certain volume of the batch reactors, we have the constant initial concentrations of the reaction with reactants will be present in the reaction environment, right? So in that initial concentration, what will be my number of moles present in the given volume of the batch reactor, right? So likewise, we need to think for the designing of the batch reactor's volume. Okay, so let's say, for example, let's say we have any certain volume of the batch reactors. Okay, so in the batch reactor, we have the presence of reactants, right? Reactants are present in the reaction environment of the batch reactors, right? So the initial, or which means some concentration is present in the reaction environment of the batch reactor, right? Now what does the concentration term means? Concentration, which means the moles of reactants present per unit volume, it's termed as the concentration, right? So first of all, we are going to calculate the volume of the batch reactor by using the zeroth order reaction kinetics, where the given rate law is minus RA is equal to K, right? K is equal to 0.04 moles per hour cubic decimeter. Okay, so let's say we have certain volume of the batch reactor in which we have initial concentration of reactants present in the volume of the batch reactor, but yet we don't know how large volume of batch reactor is required. Okay, now what does the concentration means? Concentration means the number of moles. Concentration is defined as the number of moles present per unit volume. It's termed as the concentration, right? So Ca naught. So Ca naught here represent the initial concentration of A present in the unit volume of the batch reactor, right? So concentration is the ratio of number of moles of initial concentration, initial moles present with respect to the unit volume of the batch reactor. Okay, so this is the formula. Okay, concentration is the ratio of number of moles with respect to the unit volume. Okay, so let's say in this formula we have two unknown variables, right, which is Na naught and V. Na naught represent the initial moles of A and B represent the volume of the batch reactor, right? Okay, so we have two unknowns and one known value. Ca naught is 0.4 moles per cubic decimeter, right? So let's say, then how we can calculate the number of moles present in the volume of the batch reactor, right? Na naught represent the initial number of moles present in the volume of the batch reactor. Okay, so let's say, for example, in our example, we have the molar flow rate, right? The molar flow rate, initial molar flow rates, which means the volume of the fluid which we are feeding, right, with respect to each and every time, right? So let's say the volume of the fluid which we are feeding to the reactor, it's called the molar flow rate, right? Which means the molar flow rate is 6 moles per hour, which means at each and every hour we are feeding 6 moles of reactant into the reaction environment of the batch reactor, right? So if we multiply 6 moles per hour with the charge time, right, then we'll get the number of moles present, right? So this equation, this formula is very important, right? So n naught can be calculated. Okay, so n naught is the product of molar flow rate and the charge time, right? Which means the molar flow rate units are moles per hour, okay, and the charge time is in terms of hours, right? Charge time means how much time we are taking to fill the entire volume of the reactor. It's called the charge time, right? So here the molar flow rates unit are moles per hour and the charge time unit are in hours, right? So from the numerator and denominator we can cancel out the hours, right? So finally we will remain with the moles. Okay, so by this equation we can calculate the initial concentration of the initial moles present in the volume of the batch reactor, right? By this equation we can calculate the initial moles of reactants present in the batch reactor. Okay, I hope up to here you have understood, right? Okay, now there will be a one question which will arise into our mind is, what is my charge time? Okay, okay, so let's say here the charge time is equivalent to the reaction time, which is 9 hours, right? So this 9 hours reaction time we have calculated in the previous lecture, lecture number 13, right? By using the performance equation of the batch reactor. Okay, by using the performance equation of the batch reactor for the zero theta reaction kinetics, okay, in order to achieve the 90% conversion we required 9 hours of reaction time, right? So after 9 hours of reaction time, all the 90% of the reactants have been converted into the new product, right? Okay, so from there we have obtained the 9 hours, right? Now so here we are assuming this, right? Okay, so remember this, we are assuming the charge time is equal to the reaction time, which is 9 hours. Okay, now is this always mandatory? Okay, so the answer is no, it is not mandatory, which means the charge time is is not always an equivalent to the reaction time, right? Okay, why? The charge time depends upon the availability of the operating system, right? Operating pump system, right? If the pump has the capacity of feeding the feeding at the higher flow rates, right, then the charge time will be very lower. If the pump has the capacity to feed at a very lower capacity, right, which means it will take more amount of time to fill the entire batch reactor volume, right? So the charge time depends upon the availability of the good operating pump systems, right? Okay, so it is not mandatory the charge time is equivalent to the reaction time. Okay, so remember this. Okay, so currently in order to understand, right, I am assuming the charge time is equivalent to the reaction time, which is equal to 9 hours. Okay, I hope up to here you have understood, right? Now we'll calculate the number of moles present in the volume of the batch reactor, right? So initial number of moles is equivalent to the product of molar flow rate and the charge time, right? So molar flow rate is 6 moles per hour, right? 6 moles per hour into the charge time is equivalent to 9 hours, right? So from here numerator and denominator the hours will get cancelled off, right? And if we multiply we get the answer of 54 moles, right? Which means initially we have 54 mole of reactant present in the reaction environment of the batch reactor, right? I hope up to here you have understood, right? Now so from this equation if we again see, we have the value of CA naught, right? Yes, now we have the value of NA naught, right? but there is one still unknown, which is V. So V represent the volume of the batch reactor, right? So by rearranging, we will make the subject as volume of the batch reactor, then we'll get this form of the equation, right? The volume of the batch reactor is equivalent to the ratio of number of moles, initial number of moles with respect to the initial concentration present in the reaction environment, right? So now by substituting the values of initial moles and the initial concentration, right? So initial moles is 54 moles and the initial concentration is equivalent to 0.4 moles per cubic decimeter, right? So from here, 54 moles divided by 0.4 mole per cubic decimeter. So from numerator and denominator, we can cancel out the moles, right? So finally, by calculating, we'll get the answer as 135 cubic decimeter, which means in order to achieve the 90% conversion, right, for the zeroth order reaction kinetics, where we have the given rate law as minus Ra is equal to K, right, for a single reaction where reactants A are getting transformed into the new product B, right, we required 9 hours of reaction time and 135 liters volume of the batch reactor in order to achieve the 90% conversion of the reactants, right? I hope you have understood. Okay, so here we have calculated the volume of the batch reactor, right? So the question was how large volume of the batch reactor is required, right, for the zeroth order reaction kinetics in order to achieve the 90% conversion, right? So finally we have calculated the volume of the batch reactor, which is equivalent to 135 liters, okay, and the reaction time of 9 hours we required to achieve the 90% conversion, okay, for the zeroth order reaction kinetics. I hope you have understood. Okay, so finally we have completed the calculating and understanding of the designing of the volume of the batch reactor for the zeroth order reaction kinetics. Okay, so I request you to please make these notes. Okay, now will understand for the first order reaction kinetics, right? What if I change my reaction order from zeroth order kinetics to the first order reaction kinetics, right? Then what will happen, right? So I'm going to keep all the operating parameters to be constant, right? Okay, I'm solving and I will apply the performance equation for the different reactors, right? Batch reactors, CSTR, PFR, continuous starting reactor, packed bed reactors, right? So but here in this lecture we have already calculated, right? In the previous lecture we have calculated CSTR, PFR, okay, and now we are calculating for the batch reactors, right, for the first order reaction kinetics. Okay, so similar way for the first order reaction kinetics, we have the given rate law as minus Ra is equal to Kca, right, where the rate constant value is K is equal to 0.0002 second inverse. Okay, so similar way we'll calculate the volume of the batch reactor. Okay, so let's say we need to design the volume of the batch reactor again, right? So in the certain volume of the batch reactor, what will be the concentration of the reactant present in the volume of the batch reactor, right? Now what does the concentration term means? Concentration is defined as the ratio of moles of the reactants present per unit volume, right? So concentration is the ratio of moles of the reactant present per unit volume, right? But here we have two unknown variables, which is the number of moles and the volume, right? So here we have two unknown variables, right? The concentration, we know initial concentration is equivalent to 0.4 moles per cubic decimeter, right? Now we want to calculate what is my initial with respect to the initial concentration with respect to the given molar flow rate. What will be my initial moles present in the batch reactor, right, in the reaction environment? Okay, so let's say we have the formula. The initial number of moles is equivalent to the product of molar flow rate and the charge time, right? So again, for the first order reaction kinetics, okay, we are assuming the charge time is equivalent to the reaction time, which is equivalent to 3.2 hours, right? So how this 3.2 hours reaction time came, right? So by using the performance equation of the batch reactor, we have calculated the reaction time, right, and which came up to 3.2 hours, which means in order to achieve for the first order reaction kinetics for the given rate law minus Ra is equal to Kca, we, right, in order to achieve 90% conversion, we required 3.2 hours of reaction times by using the batch reactor. Okay, so I'm assuming the charge time is equivalent to the reaction time, which is equal to 3.2 hours, right? Now, is it mandatory always the charge time is equivalent to the reaction time? So the answer is no, it is not mandatory, right? So currently, for the understanding purpose, I'm assuming the charge time is equivalent to the reaction time. Okay, now again, the charge time depends upon the operating pump system, right? If we have the good operating pump system, which means the pump has the good capacity to feed the volume of the batch feed the good volume, large volume of the feed to the batch reactor in within a few minutes or hours, right? If we have lower pump capacity, which means it will take a very huge time to fill the entire volume of the batch reactors, right? Okay, so for current understanding purpose, I'm assuming the charge time is equivalent to the reaction time of 3.2 hours, right? Okay, so let's say we'll calculate the number of moles, initial number of moles present in the reaction environment of the batch reactor, right? So molar flow rate is 6 moles per hour into the charge time, which is equivalent to 3.2 hours, right? So from the numerator and denominator, the hours will get cancelled off and we'll get the answer as 19.2 moles, which means initially in the reaction environment of the batch reactor, we have presence of 19.2 moles of reactants are present in the reaction environment of the batch reactor. Okay, so from here now we have C naught value, we also have N naught value, right? Now one thing is remaining, which is the volume. Okay, so we will rearrange this equation, we'll make the subject as volume, we'll get the final form of equation as volume of the batch reactor is the ratio of the initial number of moles with respect to the initial concentration, right? So initial number of moles is 19.2 moles, initial concentration is 0.4 moles per cubic decimeter, right? From the numerator and denominator, the moles will get cancelled off. Then by calculating, we will get the volume of the batch reactor is equivalent to the 48 cubic decimeter, which means in order to achieve the 90% conversion, right, for the by using the batch reactor, and we have the first order reaction kinetics, right, where the reactants A are getting transformed to the new product B, right? By using the batch reactor, we required 48 liter volume of the batch reactor and the reaction time is 3.2 hours, right, in order to achieve 90% conversion of reactants A into the new product, right? I hope you have understood. Okay, so here we have completed the calculation of the volume of the batch reactors, right, for the first order reaction kinetics. I hope you have understood, right? So I request you to please make all the notes. Okay, now there is one more question will arise into your mind is, right? So let's say up to here, how many terms we have used for the calculating of the volume, right? For the calculation of the volumes, right? So we have used concentration, we have used initial concentration, we have used initial number of moles, right? We have used volume of the batch reactor, and we have used the charge time and molar flow rates, right? So out of these 5 terms, let's say initial concentration is constant, right? The molar flow rate is constant. Okay, the initial number of moles is also constant, right? Okay, so no problem with all these things, right? Okay, now volume term is also okay. We are not having any problem with the term volume. Okay, now what about the charge time? This question will arise into your mind, right? So charge time, so what if I increase the charge time, then what will happen? And what if I decrease the charge time, then what will happen? This question will arise into your mind, right? So this is the correct thinking way, right, for the designing of the volume, for the design of the volume of the batch reactors, right? So let's say now what if I increase my charge time, and what if I decrease my charge time? Will it have any effect? in the volume of the batch reactors, we'll understand that, right? So let's say for understanding that, so first of all we need to understand that we are keeping the we have the constant initial concentration value, right? Initial concentration is constant. Okay, the rate constant initial concentration is constant, which is 0.4 moles per cubic decimeter, right? And the rate constant value is also constant. Okay, the rate constant value is also constant. Okay, okay, rate constant value is also constant. Okay, now we have the constant conversion of 90 percentage. Okay, xa is equal to 0.90. Okay, and we are understanding for the zeroth order reaction kinetics. Okay, okay, now what if I have the charge time of 5 hours, right? So the charge time is 5 hours, right? In the first case the charge time is 5 hours, which means uh 5 hours, 5 hours, we are using the pump system which charges the feed to the batch reactor in 5 hours, which means how many number of moles are present after 5 hours in the reaction environment, right? So let's say we'll understand by the molar flow rate. Molar flow rate is also constant, right, which is 6 moles per hour, which means for 6 moles per hour we are feeding 6 moles to the reactor, right? So with respect to each individual hour, right? So after 2 hours, in the first hour we'll have 6 moles of reactant present in the reaction environment, right? After second hour we have 12 moles present in the reaction environment, right? So likewise after 5 hour we have 30 moles present in the reaction environment. Okay, this initial number of moles can be calculated by using this same formula, right? So molar flow rate is constant, 6 moles per hour into the charge time, which is 5 hours, right? We'll get the initial number of moles as 30. Okay, okay, now by using these we have the initial number of moles and we have the initial concentration to be constant, right? By using both the terms we can calculate the volume of batch reactor, right? The volume of the batch reactor by using this formula, right? Then volume of the batch reactor will come out to be 75 liters. Okay, I hope you have understood. Now what if I decrease my charge time from 5 hours to 2 hours? Now what will happen? We are practically understanding, right, the real scenario. So let's say if I decrease my charge time from 5 hours to 2 hours, then what will happen? Then how after 2 hours, how many number of moles of reactants is present in the reaction environment, right? So molar flow rate is constant, which is 6 moles per hour, which means after 1 hour we'll have the presence of 6 moles in the reaction environment of the batch reactor. After 2 hours we have the presence of 12 moles of reactants in the reaction environment, right? So 12 moles, right? And likewise by using the initial number of moles and by using the initial concentration we can calculate the volume of the batch reactor, which comes out to 30 liters, right? I hope you have understood. Now let's say what if I decrease my charge time from 2 hours to 30 minutes, right? Then what will happen? And what if I decrease my charge time from 30 minutes to 15 minutes, then what will happen? Okay, so let's say in 30 minutes where we have 3 mole initial number of moles present in the reaction environment, right? And okay, 3 moles, and by using this initial number of moles, initial concentration, we'll obtain the volume of the batch reactors as 7.5 liters, right? Now again if I decrease my charge time, which means I am slowly steadily feeding the reactants into the reactor, right? The charge time is decreased, which means by decreasing this charge time the number of moles entering into the reaction environment will also decrease, right? So due to those reasons the number of moles will also get decreased, and due to which the number of volume of the batch reactor will the volume of the batch reactor which is filled will also get decreased, right? I hope you have understood. Okay, so let's say now in the another case, what if I increase the charge time, right? What will happen? So let's say if I increase the charge time to 24 hours, which means after 24 hours how many number of initial moles present in the reaction environment, right? So by using the same formula, right, the initial molar flow rate is constant, 6 moles per hour into the charge time of 24 the answer will, the initial number of moles come out to 144 moles is present after the 24 hours of feeding, okay, in the reaction environment, right? And by using the same formula, we can calculate the volume of the batch reactor, which comes out to be 360 volume, 360 liter volumes. Okay, I hope you have understood how, if we change the charge time, then how the number of moles and the volume of the batch reactors will vary. Okay, I hope up to here you have understood, right? So remember this, here we have kept constant, the initial concentration is kept constant, the initial molar flow rate is also kept constant, we have the constant rate constant value, right? And the conversion is also constant, which is 90% conversion, right? And we are solving it for the zeroth order reaction kinetics, which means, okay, I hope up to here you have understood, right? Now let's say for all this case, okay, now let's say for all this case, how much time will it consume in order to achieve the 90% conversion, right? This question will arise in your mind. Okay, so what, okay, so how much time will it take, what will be my reaction time, okay, for all these different cases? Okay, so remember this. So the question, now the question will arise into mind is, so what is my reaction time, right, for all these different cases? Okay, so we'll understand that. So let's say here we are solving for the zeroth order reaction kinetics, right? So we have the given rate law as minus Ra is equal to K, okay, which means the here rate of the reaction is constant, okay, which means the rate of the reaction is constant, due to which by using all these different cases we will require same reaction time of 9 hours, okay, regardlessly of having any case. Okay, for all the cases we required 9 hours of reaction time in order to achieve the desired conversion of reactants into the product, okay, in order to achieve the 90% conversion, right, where we are having the initial concentration to be constant, the rate constant value to be constant. Okay, I hope you understood, right? So we have completed this part. Okay, now one more new question will arise into my mind is, which is, when will the reaction time change in the zeroth order reaction, right? When will the reaction time change in the zeroth order reaction? How we can change this reaction time? Why for all the cases we require 9 hours of reaction time, right? This question will arise into your mind. Okay, so the answer is, so let's say the question is, I will make you understand in very simplified way how we can change the reaction time from 9 hours to any, right? Let's say I want to complete my reaction in within 3 hours, or I want to complete my reaction within 1 hour, or I want to complete my reaction within 10 hours, right? So how we can vary this reaction time, we need to understand that. Okay, so the answer to the question is, by changing the initial concentration, we can change the reaction time. So how? We'll understand that. Okay, so let's say initially we have the initial concentration to be 0.4 moles per cubic decimeter present in the reaction environment of the batch reactor, right? Now, what if I develop the initial concentration from 0.4 to 0.8 moles per cubic decimeter, right? Then what will be my reaction time? Okay, so by doubling the initial concentration from 0.4 moles per cubic decimeter to 0.8 moles per cubic decimeter, the reaction time will also get double ups. Okay, so the reaction time from 9 hours to 18 hours, right? So reaction time will also get double up from 9 hours to 18 hours, right? So how? We need to understand that. Okay, so how, by doubling the concentration, how my reaction time also develops, right? Even for the same zeroth order reaction, I am not for the same zeroth order reaction, we don't have the concentration value in the reaction rate, right? We don't have the presence of concentration term in the rate law for the zeroth order reaction kinetics. Then how, by doubling the concentration, the reaction time develops? We need to understand that. Okay, so let's say we'll understand that. Okay, so recall the fundamental concept of the batch reactor, the performance equation of the batch reactors, right? So here this formula represent the performance equation of the batch reactor, right? So T is equal to C naught integration of 0 to xa dxa upon minus Ra. Okay, now observe these and analyze that the T represent the reaction time, right? So the reaction time is the function of concentration, conversion, and the rate of the reaction, right? Now here in these, the rate of the reaction is constant for the zeroth order reaction kinetics, right? Okay, the conversion is also constant for the zeroth order reaction kinetics, which is 90%, right? Okay, so we have only one variable term, which is CA naught. Why CA naught? Because in this case we have double up the CA naught, right? Initially we have the CA naught value as 0.4 moles per cubic decimeter. Now in this case, in order to understand how we can change the reaction time, right, for the zeroth order reaction kinetics, so we have double up the initial concentration from 0.4 to 0.8, right? Which means we have the direct relation of reaction time with the constant initial concentration, which means if we increase the initial concentration, then reaction time will also increase. Okay, and if we decrease the initial concentration, then the reaction time will also get decreased, right, due to the direct relation of reaction time with the initial concentration. I hope you have understood, right? So due to those reasons, if we develop the initial concentration from 0.4 moles per cubic decimeter to 0.8 moles per cubic decimeter, the reaction time will also gets developed from 9 hours to 18 hours, right? Which means in order to achieve the 90% conversion, right, the batch reactor will require 18 hours of reaction time in order to achieve the 90% conversion of reactants A into the product. I hope up to here you have understood, right? Okay, now again you will be very curious and the new question will arise into your mind is why zero order behaves this way. This question will arise into your mind. Okay, so we'll understand that. So let's say, okay, so why this behavior is being observed in the zeroth order reaction kinetics? Okay, due to the reason for the zeroth order reaction kinetics, we have the rate law is constant, right? Minus Ra is equal to K. The rate law is constant, which means the rate is the rate of the reaction is constant, right? The reaction rate is constant. Due to those reasons, we are observing these phenomena, right? By doubling the initial concentration, the reaction times also double ups, right? So we'll understand why. Because the rate of the reaction is constant, which means the reaction consumes fixed moles per unit time, right? The reaction consumes fixed moles per time. Due to those reasons, we are observing the doubling in the reaction time by doubling the initial concentration. Okay, which means if we have more concentration present in the reaction environment, which means the batch reactor will take more time to consume all those reactants and get converted into the new products, right? To achieve the 90% conversion. Okay, if we have less concentration present in the reaction environment, which means the batch reactor will consume less time to convert 90% of the reactants into the new product, right? Due to we have the zeroth order reaction kinetics where the rate of the reaction is constant. I hope you understood, right? Okay, now there will be one more question which arises into our mind is for zeroth order kinetics, the rate law does not contain concentration, right? For the zeroth order reaction kinetics, the rate law does not contain the concentration, right? Then why changing the concentration changes the reaction time? Okay, this question will arise into your mind. So now we are dwelling more deeper into the fundamental understanding of the designing of the reactors, right? So let's say why it is so. So I will make you explain all these things in a very simplified way, right? So let's say, for example, if we have a plant area 1 where we have kept number of boxes, right? And we need to transfer those boxes to the entrance gate of the plant 2 area, okay, by using the conveyor belt. Okay, now the conveyor belt analogy is it can transfer 10 boxes per hour, right? Conveyor belt analogy, which means the capacity of the conveyor belt to transfer the boxes is 10 boxes per hour, which means per hour conveyor belt will transfer 10 boxes from plant 1 area to the entrance gate of the plant 2 area, right? Okay, I hope you understood. Okay, now let's say if I want to transfer 50 boxes from the plant 1 area to the entrance gate of the plant 2 area by using the same conveyor belt, then how much time will it take? Right, it will take 5 hours of time, okay, to transfer the boxes from plant 1 area to the boxes to the entrance gate of the plant 2 area, right? Okay, now what if I double up the number of boxes from 50 boxes to 100 boxes, right? Now here we are doubling the concentration of the boxes, right? So what if I develop the concentration of the boxes from 50 boxes to 100 boxes, then what will happen to the reaction time, or the in how much hour will the 100 boxes will get transferred, right? So the same way for the 50 boxes, the conveyor belt requires 5 hours of time, right? And so if we double up the boxes from 50 to 100, then in order to transfer the 100 boxes from the plant 1 area to the entrance gate of the plant 2 area, the conveyor belt will require 10 hours of time. Why? Because the conveyor belt analogy is, the conveyor belt capacity is, it can transfer 10 boxes per hour, right? In order to transfer 100 boxes, the conveyor belt will require 10 hours, right? So for the 50 box transfer, the conveyor belt required 5 hours. For the 100 box transfer, the conveyor belt required 10 hours, which means by doubling the initial concentration from 50 boxes to 100 boxes, the reaction time also gets double up. Why? The only reason is due to the speed of the conveyor belt, due to the capacity of the conveyor belt, okay, which means due to the speed of the conveyor belt, which means the conveyor belt can can't transfer 10 boxes per hour, right? The speed is constant, okay, regardlessly of having a very higher concentration or lower dilute concentration, which means if we have the higher concentration, then also the conveyor belt at the same speed it will transfer the boxes from plant 1 area to plant 2 area, right? And if we have the very lower concentration present in the plant 1 area or in the reaction environment, at the same speed the conveyor belt will transfer those boxes into the plant 2 area. I hope you have understood. Okay, due to the capacity of the conveyor belt is same, is constant, which is 10 boxes per hour. So due to those reason, right? So if we develop the, due to the zeroth order reaction kinetics, we have the constant reaction rate, which means we have the constant speed of consumption of reactants, right? So due to those reasons, it doesn't matter if we have the higher concentration present in the reaction environment, okay, and it doesn't matter if we have a very dilute concentration present in the reaction environment, right? Then it will take the same time. Okay, same time means it will take the same, it will at the same speed it will consume those reactants, right? So let's say if we have higher concentration present in the reaction environment, then we have the constant speed, right? Due to constant speed, the batch reactor will take, due to the higher concentration, right, present in the reaction environment, the batch reactor will take more time, okay, because we have the constant speed of the consumption, right? So if we have the higher concentration, then the rate of the reaction will take longer time to consume those reactants, to consume all those reactants, right? And if we have the lower concentration, then the batch reactor, right, for this growth of the reaction kinetics, the batch reactor will take lower time, right? Because here the speed is same, right, regardlessly of having the higher concentrated or dilute concentration. Okay, I hope you have understood, right? Okay, so here we have calculated the understanding of the zeroth order reaction and the first order reaction for the batch reactors, right? So we have understood how we design the volume of the batch reactors for the zeroth order reaction kinetics and for the first order reaction kinetics, right? So I request you to please make all the important notes, right? Okay, now let's say, so up to this point we have designed the CSTR, PFR, and the batch reactors, right, for the first order reaction kinetics. Okay, now we are designing the packed bed reactor, right, for the first order reaction kinetics. Okay, so we'll understand how we design how much weight of the catalyst is required for the packed bed reactors, right? Because the packed bed reactor is also a tubular reactor, right? But the tubular reactor in which we have the hollow space, right? So that hollow space is entirely completely filled by the packing materials, right? So it's termed as the packed bed reactor. So how much, or the weight of the entire hollow space is filled with the catalyst, right? So how much weight of the catalyst is required in order to achieve the 90% conversion, right? In order to achieve the 90% conversion by using the packed bed reactor, how much volume, or sorry, how much weight of the catalyst is required in order to achieve the 90% conversion, right? So let's understand that. So first of all, we need to write the performance equation of the packed bed reactor, right? The performance equation of the packed bed reactor is given as W is equal to Fa naught integration from 0 to Xa dxa upon minus Ra, right? So we are solving it for the first order reaction kinetics, where the given rate law has minus Ra is equal to Kca, where K is equal to 0.002 cubic decimeter hour per kg catalyst, right? Okay, so I hope you have understood. Okay, so let's say, okay, you understood, right? So we are keeping all the operating parameters to be constant, right? We are keeping all the operating parameters to be constant. We are designing the packed bed reactor for the first order reaction kinetics, where the reactants A are getting transformed into the new product B, and we are aiming for the 90% conversion by using the packed bed reactor. So the question is, what amount? So the question is, how much amount of catalyst we required in order to achieve the 90% conversion. Okay, so let's say, so here W is equal to Fa naught integration from 0 to Xa, right? From 0 to Xa dxa upon Kca, right? So we are substituting the minus Ra is equal to Kca, right? So here again, recall, we have the two forms of Ca, right? So which form we are going to use, I already explained in the previous lecture, right? In these lectures, right? So we'll use the second form of Ca, which is Ca is equal to 0, Ca is equal to Ca naught into 1 minus Xa, and the first form was Ca is equal to 0.1 Ca naught, right? So for the deriving of the performance equation for the reaction rate, for the designing, right, of the reactors, we will use the second form of the Ca, which is Ca is equal to Ca naught into 1 minus Xa, right? Okay, so W is equal to Fa naught divided by the rate constant value is constant, right, which is 0.0002 cubic decimeter per hour kg catalyst, right? Okay, which means the rate constant value is constant, right? So W is equal to Fa naught, we are taking K out of the integration, so K we have took out of the integration, right? Ca is equal to Ca naught into 1 minus Xa, so Ca naught is also constant, which is 0.4 moles per cubic decimeter, right? So due to those reasons, we are taking K and Ca naught out of the integration. Okay, so W is equal to Fa naught divided by K Ca naught integration from 0 to Xa dxa upon 1 minus Xa, right? So the solution of this part, right, is already we have understood in the previous lecture, in this previous session, right, where if we solve this integral form, then we'll get the answer as minus ln 1 minus Xa. Okay, so W is equal to Fa naught into minus ln 1 minus Xa divided by K Ca naught, right? Now we'll substitute all those values. Okay, so molar flow rate value is 6 moles per hour, minus ln into 1, and conversion is 0.90, K is 0.0002 cubic decimeter per hour kg catalyst, and Ca naught is 0.4 moles per cubic decimeter, right? So from here, numerator the moles and denominator the moles will get cancelled off, the hour will get cancelled off from the denominator and numerator, right? So this is in denominator to denominator, so hour will come into the numerator, and here we have the hour in denominator, so this will come here, right? So now I hope you have understood, right? And the cubic decimeter will get cancelled out from the numerator and the denominator, so we are remaining with the kg catalyst, right? So if we solve this, then how much weight we'll get? We'll get 1,72,693.82 kg catalyst, which means we required weight of the catalyst is 1.727 into 10 raised to 5 kg catalyst, right? Which means a very huge quantity of catalyst is required, right, in order to achieve the 90% conversion, right? 90% conversion, right? This is a very large value, right? So why we obtain this large value? We need to understand that, right? So this question will arise into your mind, right? So why, if we are using the backbed reactor, then why such a big amount of catalyst we required in order to achieve the 90% conversion, right? The answer is, you can guess, then please comment below, right? The answer is because due to a very smaller value of the rate constant, right? Due to the smaller value of the rate constant, we are getting a very large value in weight of the catalyst. Okay, so what does it mean? We'll understand practically. Okay, so let's say here the rate constant value is 0.0002 cubic decimeter per hour kg catalyst, which means we have a very smaller value of rate constant, right? So for the first order reaction kinetics, the reaction rate is in direct proportion to the rate constant and the concentration, right? So here the concentration is constant. Okay, Ca is constant, right? Okay, so but here K, the rate constant, so reaction rate is in direct proportional to the rate constant, which means if we have the lower rate constant value, which means the reaction rate will be also lower, right? Will tends to lower, decrease, right? So due to those reasons, we required a very large amount of catalyst in order to achieve the 90% conversion, right? Now the question will arise into mind is how I can increase the reaction rate, right? And how I can decrease the amount of catalyst required in order to achieve this 90% conversion for the same first order reaction kinetics by using the backbed reactor. This question will arise into mind, right? So this is exactly where we will utilize the fundamental concept of the backbed reactors, right? So let's say, and the chemical reaction engineering, right? The fundamental concept of the chemical reaction engineering. Okay, so let's say, if let's say by observing, we have the first order reaction kinetics, we have the rate law is minus Ra is equal to Kca. So let's say if I increase my rate constant from 0.0002 cubic decimeter per hour kg catalyst to, let's say, 31 cubic decimeter per hour kg catalyst, right? So I increase my rate constant value from 0.0002 to 31 cubic decimeter per hour kg catalyst, right? So by increasing the rate constant value, right, which means by increasing the rate constant value, the reaction rate will also increase, right? Due to which we will require a very small weight of the catalyst, okay, in order to achieve the same conversion of 90%, right? So if we increase the rate constant value to 31 cubic decimeter per hour kg catalyst, now by solving these, by a similar way, by solving these, we will get the weight of the catalyst, which is 1.11 kg catalyst, right? So do you see a very drastic change, right, in the amount of the catalyst requirement, right? First of all, in the first case where the rate constant values are low, we have a very huge amount of catalyst, right, which is 1,72,693.882 kg catalyst we required in order to achieve the same 90% conversion, right? But if I increase the rate constant value from 0.0002 cubic decimeter per hour kg catalyst to 31 cubic decimeter per hour kg catalyst, then the amount of the catalyst required will be very small in order to achieve the same conversion of 90% by using the first order reaction kinetics for the packed bed reactor, right? So where by using this rate constant value of 31, we'll require 1.11 kg catalyst, okay, and we'll obtain 90% conversion, right? Okay, I hope you have understood, right? So due to the lower rate constant value, and we require the higher conversion, right? So due to those reasons, we require the higher weights of the reaction, a higher weight of the catalyst, right? And if we have the higher rate constant value, then we require, and in order to achieve the same high conversion of 90%, we require lower weight of the catalyst, right? For the first order reaction kinetics. I hope you have understood, right? So I request you to please make all the notes, right? Okay, and you can make all the notes in your language also, right? So I request you to please make all the notes, okay?